So this video is looking at collision theory and kinetics and interpreting Maxwell-Boltzmann distribution curves. So collision theory, so a chemical reaction is a simple rearrangement of the atoms present. The faster this happens, the faster the reaction rate. So for some particles, say you've got a particle here and a particle here, for them to react they have to collide. They have to collide at the correct orientation and also with the required activation energy. So if they're both moving towards each other, then their combined energy must be at least the required activation energy for the reaction to take place. So actually there are millions and millions of collisions that take place every second, but actually very few of them result in a reaction because of the fact that the one, they're maybe not in the correct orientation, or two, maybe the particles don't have enough energy, combined energy, even though they are hitting together, they don't have enough combined energy. Just a quick definition for you, so collision energy is the combined energy of both particles. So collision theory and the whole study of kinetics is all looking at what factors we can do, what we can change to make a reaction faster. So a quick little diagram you might remember from GCSE, so it shows our reactants and our products, and it shows that to get to our products we have to add in the activation energy. So that's the particles colliding together with the required activation energy, okay, and then turning into the products. You might remember from GCSE that this is a one showing an exothermic reaction because you can see more energy is released than is taken in to form the transition state. So we're going to look at something called a Maxwell distribution curve. So this looks at the energy that different gas particles have. So if you imagine you've got a load of gas particles, some of them are going to have lots of energy, some of them not much energy, but there's going to be a sort of average point. So before we plot the curve, which needs a few little facts. So one fact is that no particles have zero energy. So a particle with zero energy would have a temperature of 0 Kelvin, and that doesn't exist naturally in the universe. So here is the Maxwell distribution curve. So in a Maxwell distribution curve, the area under the curve represents the total number of particles in the sample. So the highest point of the curve, this is the most probable energy. So if you had 100 particles and you pick one at random out of a hat, you're most likely to pick up one out which has an energy here. It's the most probable energy. So when you heat up a sample of gas, what happens is the Maxwell distribution curve, the shape changes. So first off, the most probable energy, you can see it's shifted to the right. We can see at this higher temperature that more particles have the higher energy, the highest energy. So on a Maxwell distribution curve, you can mark in the activation energy. So this is the energy required for the reaction to take part. So any particles which have at or above this energy are able to react. They have the minimum energy needed for a collision to be a reaction. So the particles on the other side of the activation energy have too little energy to react. The particles in purple have enough energy to react. So let's look at what happens when you increase the temperature. So we're comparing a low temperature and a high temperature. So this is the low temperature, and this curve here is at a higher temperature. So you can see as you increase the temperature, the most probable energy, that's this point here, the highest point, shifts to the right. The number of particles with the most probable energy decreases. Why is this? Well, when you increase the temperature, you can see that there's more particles with the higher amounts of energy. So there's actually a greater spread of energies. So therefore, because there's a greater spread, there's going to be less particles with any one particular energy. We can see that when we increase the temperature, there are now more particles, there is a larger area under the curve above the activation energy. So therefore, more particles have the required activation energy to react. What about a catalyst? So when we add a catalyst, what happens, it doesn't change the shape of the curve. All it does is it moves the activation energy. So you can see the activation energy has been shifted to the left, and now more particles have the required activation energy. So what about concentration? Well, if we halve the concentration, what do you think is going to happen? Well, if you halve the concentration, you're going to get the same curve, so the same shape, except this time you've got half the number of particles. So therefore, the area under the curve is going to be half that of double the concentration. What about pressure? Well, think, what happens when you increase pressure? Does it change the energy? If you increase pressure, is more energy created? So we're talking about having basically an increase in pressure means using a smaller volume. That doesn't change the actual amount of energy. You can't create energy just by having a smaller volume. Does it change the number of particles? Having a higher pressure doesn't change the number of particles. So therefore pressure does not affect the Maxwell distribution curve. Now, there's only one way I think they could ask pressure in a slightly difficult way. If they said the pressure was increased but the volume was kept the same, this must mean the only way for pressure to be increased is by having either a smaller volume container or having more particles. So if the question says that they've increased pressure but the volume, the container is still the same size, the only way they could have done that is by adding more particles. So therefore, if the question reads like that, an increase in pressure in the same volume would mean the same as an increase in concentration.